Cambridge University Press, we would like to welcome you all for today's webinar. I will also take this opportunity to talk very briefly about the press. Cambridge University Press is part of the University of Cambridge and is one of the world's oldest publisher. Our India Publishing Center was set up in 2012, and in this region, we are a fairly young publisher. Our portfolio consists of high quality academic and higher education content in science, technology, mathematics, and social sciences. We also publish in exciting and innovative new physical and digital formats and are known for the best learning and research solutions. The topic for today's webinar is engaging UG physics students in pedagogical and research projects. We are thankful to Professor P.C. Deshmukh for agreeing to speak about this important topic. Professor Deshmukh is adjunct professor at IIT Tirupati. He has taught a wide spectrum of physics courses at the undergraduate and graduate levels and published more than 100 research papers in many international journals. He is the author of Foundation of Classical Mechanics, published by Cambridge University Press. It is acclaimed as a unique work because of its approach and content. His book is available on open access till 10th of July, so I encourage all of you to visit cambridgecore.org and make most of it. In today's session, Professor Deshmukh will share his joyful experience of working with undergraduate physics students and how this exposure was extremely beneficial for the students. He will also emphasize on how such projects provide a great opportunity to both teachers and students to enjoy physics as a subject and rigorously learn its theoretical and experimental methods. Before we start, there are few housekeeping announcements. Professor Deshmukh will speak for about 40 to 45 minutes, and then we shall have a brief question and answer session. You can write your questions in the chat box during the session. Use the chat box only for asking questions. Whenever you are writing some questions in chat box, please select for all the panelists and attendees so that it is visible to everyone. Your cameras and microphones are kept off to save bandwidth and to conduct the session smoothly. Now let's begin the session. Dr. Deshmukh, over to you. Dr. Deshmukh?
Can you all hear me?
Yes, sir, we can hear you now.
Okay, good. All right. So greetings and hello to everybody. Thank you all very much for joining this afternoon. And I'm very grateful to the hosts, to the Cambridge University Press for giving me this marvelous opportunity to celebrate a good number of undergraduate projects, which I have worked with a number of students. You see their faces on this opening slide, and I will be talking to you about the joy of having worked with these students over here. And at the end, I will also be happy to take a few questions. So having been a teacher at IIT Madras for more than 3 decades, and then subsequently, I also had opportunity to work at some of the other institutions, including IIT Mandi, where I was on deputation for some time, and later at IIT Tirupati. And at Tirupati, I also had an opportunity to be an adjunct faculty at the ISER, the Indian Institution for Science Education and Research at Tirupati. So I got an opportunity to work with a number of students at IIT Madras and IIT Tirupati, and also the ISER Tirupati, and many of them are represented over here, and not everybody is represented over here. So let me begin with sharing this excitement of what science and engineering is today. And it is really very young, means considering the age of the universe or the life of man on Earth. And until quite recently, even as recent as 2000 years, means on this time scale, you have to consider 2000 as quite recent. And at this time, the Greeks thought that, okay, things fall on Earth when you throw them up, because the Earth is the natural abode of things, and things fall just as horses return to their stables. And this was quite an accepted, explanation of the way things really happen. And then it is only a few hundred years ago, with the experiments of Galileo in the 16th century, that we started having an understanding of the natural phenomena in terms of what we call as modern science. So the science as such is really very young. But then in just these few hundred years, how much have we learned? We have learned about how things fall, that a small mass and a large mass get accelerated together toward the Earth. And then we know a lot about how the universe was born, and how we, of course, there are many questions which are yet to be answered, but then there is a lot that we know, and that is amazing. That from the time of, Kepler, Newton, and Galileo, and come to modern science, our understanding of the universe, quantum theory, and now we are in the age of quantum computation with IBM, Google, and Honeywell all competing for the top spot for making advancements in quantum computation, which will really revolutionize life on Earth much beyond what we have experienced in the last 100 years, which already has been really amazing. So how do we bring up the students from, the times of Kepler, Galileo, Newton, right up to, acquainting them with advances in quantum theory, cosmology, and so on. And in a short span of time, in the few years that these students are at the undergraduate level, you have to bring them up from the basics of classical physics, the physics of Galileo, Kepler, Newton, and so on. And you cannot really bypass that. And you begin over there and then bring them up to what is modern science, modern engineering, and modern technology. So this was a question which always used to concern me as a teacher. And one of the things that I enjoyed very much, and I will introduce you to the very first such project which I took up in this context, and you will see how far it goes, which is just the Newton's law. We often look at Newton's law as F equal to dP by dt, but then when you consider how it should be interpreted and applied, given the fact that the Earth is rotating, and what that does is that the northern edge of your room's floor moves eastwards slower than the southern edge because of this geometry. And this has got some very dramatic effects. And these need to be really studied at the undergraduate level. And I'm sure many schools and colleges and universities do that. But how important it is, it deserves much more than a mention. And I will share with you some of the important consequences of this phenomenon. For example, if you launch a missile at the North Pole and it is targeted at the equator, just imagine how far the Earth would have moved during the flight of this missile. And I'll let you work this out as a small calculation. It's a very interesting calculation. And this is the kind of problem which I asked some of my undergraduate students to take up. They were first year students just out of high school, and look at the consequence it would have on navigation of an aeroplane, the missiles, then the long-range missiles, the intercontinental ballistic missiles, and this entire technology of navigation, aviation, and also communication and networks. All of this is affected by this particular phenomenon, which requires interpreting Newton's law F equal to dp by dt in a rotating frame of reference, which is the Earth. There is also an urban legend that at the Battle of Falkland, between the British and the Germans, the British shots landed somewhat away from their targets because the calculations of the Coriolis term, which needs to be taken into account in this analysis, was going wrong because it was done because this was on the southern hemisphere where one has to account for this correction appropriately. Now that perhaps is an exaggeration, but it certainly dramatizes the importance of this effect. And then there are other consequences. For example, the length of the day has actually decreased by 1.8 microseconds as a result of an earthquake 2011 in Japan. This was a 9 Richter earthquake, and this is what happens every time there is an earthquake. So there have to be these corrections which have to be made to the atomic clocks. And if these are not properly calibrated, you can have devastating effects of what is happening with your day-to-day life. For example, on the 30th June 2012, this was 8 years ago, trading on the New York Stock Exchange had to be suspended because the atomic clocks were not properly adjusted to take account of the fact that the Earth's rotation speed has to be properly taken into account. And this is a correction which is called as a leap second correction. We are all familiar with the leap year correction, but there is also a leap second correction. The last leap second correction was done on 31st December 2016. And the next was to be done just about a week ago on 30th of June this year, just less than a week ago, but I think they decided not to do it. And this is decided by this IERS, the International Earth Rotation and Reference System. So this is how far the technological impact of these corrections are important. And it is very important for the undergraduate student today to understand this very thoroughly. And what one has to do is to solve this differential equation, which looks somewhat complicated, and I'm not going to explain this term. You will find them in many other sources of literature on undergraduate physics. But this is the equation which Gopal Pandurangan, an undergraduate student, he started working on it when he was a first-year student of computer science at IIT Madras, and he started working on this. And this is what Gopal is. This was 30 years ago. Gopal is now a professor of computer science at the University of Houston. He has published this book on wireless algorithms and so on. He's a very distinguished scientist, but this was his first project. And this is what he says about his project. Since today's webinar was planned several weeks in advance, I took the opportunity to contact many of these students who worked on these projects with me, and they sent me some messages which I'm sharing with you. So this is Gopal's message. He says that this was 30 years ago, and he says this was one of the best things that happened to me at IIT Madras. And even during my undergraduate years, I was glad that it was used as an experiment. It was a simulation experiment set up in the physics lab. And then he goes on to say that looking back, I would say this was my first research experience, and it played a role in me getting into full research career. So let us hear Gopal directly saying this. He has sent me a video clip, which I'm sharing with you now.
I mean, that I still remember, probably one of the few things that I really recall fondly from my undergraduate days at IITM. So I think doing research projects in undergraduate, when you're doing your undergraduate, is a great way to get into research, to talk and interact with professors and other students.
I hope you could hear Gopal, and let me go on, and let me
Professor
tell you,
Deshmukh?
yes.
Professor Deshmukh, sorry to interrupt you. We would like you to switch on the camera. We are very interested in seeing you as well. Could you please do that?
Oh, all right. So let me see. Oh, I did not know that it was off. All right, here, let me do it now. Okay, can
I'm sure the
you,
audience is
all right.
interested in seeing you as well.
Yes, yes, I'm here. Are you able to see me? And
Yes,
could you see
perfect.
Gopal's video also?
Yes,
Very
very
good, thank
nicely.
you.
Yeah,
Yeah.
thank you.
So let me continue with the discussion here. And one very important foundation of classical mechanics, which all physics researchers and scientists and engineers feel undergraduate students must be acquainted with, is the alternative formulation of classical mechanics, not based on the Newtonian principle of causality and determinism, but on the principle of variation due to Lagrange and Hamilton. And this is an extremely important alternative formulation of classical mechanics, which really needs to be taught. There are a good number of papers in the American Journal of Physics advocating that this should be introduced at an early age. And this, in fact, becomes the forerunner of an alternative formulation of quantum theory. Means everybody knows the formulation of quantum theory due to Schrödinger and Heisenberg, but the alternative formulation of quantum theory, which is Feynman's path integral approach to quantum mechanics, is also, it draws its inspiration from the principle of variation, which is why it is so important to be introduced at an early age. And I thought that it best to do this introduction, to introduce this important idea by involving some undergraduate students in a physics project. And this is a project which was carried out at IISER Tirupati, and Parth, Abhiya, and Vaishak constructed these models. These are models, as you see, various shapes. One of these is what is called as the brachistochrone, and it is about how things move under gravity. So I will not get into the physics of this. In fact, they managed to publish a pedagogical paper in the Resonance, and I will invite viewers to see this paper to get the details. But what is exciting is that these young students were able to come up with, they discussed the physics, constructed a model, carried out experiments, measured, and convinced themselves that, okay, this is how the theory really works. And this was a very exciting way of introducing this alternative foundation of classical mechanics. So let us hear what Parth has to say about this experience. So I'm introducing Parth here.
The journey of building the model and learning theory behind the Brachistochrone model was very exciting, but as well as challenging at the same point. And building model was a really laborious task, but also satisfying at the same time, because when you overcome the experimental hurdles, you feel good about it. And this project taught me how to do experiment correctly, and what can be the challenges while performing the experiment, and how to write a research paper.
So thanks to Gopal and Parth for sharing their experiences of working on this project. And many institutions recognize the importance of involving undergraduate students in projects of this kind. As a matter of fact, I would like to mention just a few, like the Council on Undergraduate Research, which is an international organization of individuals, institutions, and they have got members all over the world. And their mission is to encourage undergraduate research for high quality mentored undergraduate research and scholarship and creative inquiry. So there are many institutions, organizations, and even in India, many of the universities and certainly the IITs and ICERs have a regular program on that. But one of the objectives of today's webinar is to highlight the fact that whereas quite a bit is being done, more needs to be done. So let me now share with you another experience, which is where I am involving these undergraduate students who have worked with me. And I would like to begin with a quote which says, "No other place in physics where such a simple and accurate general principle requires for its real understanding an analysis in terms of two different phenomena." Now, this is a very strong quotation. And this, in fact, becomes, this brings us to the physics, which is so important that it is involved in the theory which was subsequently developed by Einstein. The special theory of relativity is intimately connected to what Feynman is alluding to. This quotation is from Feynman lectures, and this relates to the Faraday lens relation. So again, I will not get into the physics, which is very exciting, but you can read about it in a paper which was eventually published in Resonance. And this was done by two students who are now young men. This was also, again, almost 30 years ago, Satish Krishnamurthy and Venkatesh. Venkatesh is now a professor at Stony Brook, and Satish is in the Silicon Valley in California, and is a founder of some IT companies. So he has had a very successful career. And this is what they have to say about their project. That when we look back at our undergraduate special project experience, we recognize that our project really helped us develop a foundation for lifelong passion for combining computation with theory in our own professional setting. So what they did really was to develop a computer simulation of the dynamics of charged particles in electromagnetic fields, and then they showed how their observations are connected with the special theory of relativity. So this is an amazing experience. It's a very important concept, a very fundamental concept, and it was wonderful to have these young students to grasp the physics behind it, develop the algorithm, do the numerical work, do the coding, do the graphics, and they learned so much in the process. And they go on to say that it has shaped our professional journey and careers in a profound way that we simply could not have imagined at that time. So here is a message for the young students who are in the audience this afternoon, that get involved in some projects of this kind. I want to hear, I want you to know this directly from others who were students like you at one point of time and who have achieved so much after decades as they have learned. So let me share with you their comments in their own voice. So here I'm pulling up the video which Satish and Venkatesh recorded for us. So Satish and Venkatesh now.
What we think is that going forward, bringing theory and computation together will help us all solve a lot more of the problems facing humanity than what we have been able to do so in the past. And I'll now request my friend, Professor Venkatesh, to say a few words about this as well.
Thank you, Satish. Of course, I also very much enjoyed working on the project as an undergraduate student. And little did I know that, you know, the little experience that I had as an undergrad would inspire me and continue to keep me interested in understanding how computational approaches can be used to solve problems in the engineering and the scientific world.
Yeah, so I'm really very grateful to all these students who are former students. They are now my colleagues, and some of them are almost teachers because I learned so much from them. And but it is good to hear directly in their own voice, and I made them a part of this webinar by requesting them to share these video clips. So here is another experience. This is a recent one from IIT Tirupati, and the special theory of relativity, which I mentioned, which many physics students get exposed to only in their graduate studies and only marginally at their undergraduate level. So Satish and Venkatesh did this marvelous simulation experiment and showed how it is connected with the special theory of relativity, how the charge particle dynamics is connected with the special theory of relativity. And here is another experiment which was set up at IIT Tirupati by these young students, Jnaneshwari and Niharika, which is again connected with the special theory of relativity. But this time it is an experimental demonstration. It is a tabletop demonstration of the relativistic time dilation and length contraction. So they set up an experiment which they eventually published in the Indian Association of Physics Teachers Bulletin. And I would like you to hear what Jnaneshwari has to say about her experience. She says, it provided an opportunity to discover my abilities and help to improve my confidence, patience, and time management skills. So let us hear Jnaneshwari directly.
We could see the decay tracks in the cloud chamber, which revealed many aspects of cosmic showers, including neon decay. In spite of many challenges, we could carry the experiment with outstanding success.
So this is the main thing. This is the main thing. The experiment was tough and they had many challenges, and eventually they succeeded. And it is really very important that this kind of experience is gained at such a young age. And I'm sure that Jnaneshwari and Niharika will also go a very long way in their respective careers. So research as such, it is in some sense systematic gathering and analysis of information to create new knowledge. And this is something which every new generation will have to continuously do and improve upon what the earlier generations did. And what undergraduate research helps is to test the determination, the perseverance. It develops creativity, intellectual independence, and there is so much to gain by getting involved in undergraduate research. So here is another example which goes beyond the special theory of relativity. It now gets into the general theory of relativity. And this is a simulation done by Kaushal at the IISER Tirupati. And what he did was to study a very dramatic effect of Einstein's field equations of the general theory of relativity, which explains the precision of the Mercury orbit about the sun. It's a very tiny precision, just a very small fraction of a degree over a whole century. It's such a small effect, but then this is what detailed physics is really about. And Kaushal went on to publish this result in a journal, Resonance in Resonance in 2017. And let us hear Kaushal's experience here. So Kaushal now.
So research process is a step-by-step thing. First you think of an idea or come up with a hypothesis, then you test this idea or hypothesis using computer simulations or observational data, or you come up with a new experiment to test this hypothesis. Secondly, it also teaches you that failure is part of research. Sometimes your computer programs don't work, sometimes your experiment goes wrong, and that is okay. The important thing is to come up with new approaches using your knowledge and experience to tackle such problems.
So I'm really glad that I had these students come back and narrate their experiences, because, you know, the way Kaushal puts it across, that yes, there are moments of failures, there are things go wrong, your experiment doesn't work, your theory doesn't work, but the important thing is to keep advancing. And then look at what they have succeeded with, which is to really solve, although in an approximate manner, Einstein's field equation and account for a small effect on Mercury's precession about the sun. So here is another picture which came as a consequence of my introduction to the theory of chaos to first year students at ISER Tirupati. And I talked about fractals, and the students went on to build models of the Menger sponge, which is a fractal of dimension between 2 and 3. And here are these ISER students building this model. In fact, they built 3 models. They even gifted one to ISER Pune, I think. I see Vaishak over here, and there are 3 others. And another student in the same class, Abia, she got interested in the theory of chaos, and she decided to get into some experimental work. And we chose to take up some experiments in chemical reactions in which you can observe chaos. So she tells us that we designed 3 experiments, and then she did simulation work and did a good amount of computational work. And this is something that she published again in Resonance. This paper came just quite recently, a few months ago in March 2020. And what she tells us is that through the long journey of this project, I gained experience in various skills like scientific writing, coding, numerical analysis, and communication skills. And I really admire the patience and the perseverance of Abia, because this was a very difficult project. It required her to go to IIT Madras. She worked in the laboratory of some of my friends and colleagues, former colleagues at IIT Madras, and collaborate with them. And all of this really benefits undergraduate students in a very big way. So I pulled out a few points to share with you, which is the benefits which undergraduate students get through such research projects. It enhances student learning, develops critical thinking, creativity, problem-solving skills, intellectual independence, promotes innovation-oriented culture. So there are great advantages. And the institutions where these students study, the universities, they also benefit from these presentations. You see that all of these projects have actually been published in various pedagogical journals. Everything is not research as to bring out a new result, but it does bring out a new result in a new way. And that is what makes it publishable in a pedagogical journal. So the university also benefits from these presentations. They increase their visibility. So let me give you an example of 2 papers which this undergraduate student, he was actually at Amrita University in Coimbatore, and he came all the way from Coimbatore to Chennai to work with me at IIT Madras. And he started, he was a first-year electrical engineering student when he started this work, and then kept visiting during vacations, weekends, and so on. And by the time he graduated from Amrita University, with a degree in electrical engineering, he had published these 2 papers, in Journal of Computational and Theoretical Nanoscience, both on scattering of electrons of cylindrical potentials, which like mimics a nanotube and also a multi-walled nanotube. This is Vivishek Sudhir, and he is now at MIT. With the 2 papers that he wrote as an undergraduate student was just the beginning of what is a brilliant career for Vivishek. And he tells us that it helped me realize that I enjoyed the uncertainty that is pervasive in research. Yes, there is uncertainty, and it is important to be able to cope up with it and find it exciting and, in fact, even inspiring. And Vivishek tells us that year and the ensuing 3 years were by far the period that shaped my approach to physics, plus every day was an opportunity to learn something new. So this is the kind of excitement undergraduate students get when they get involved in projects of this kind. So like I mentioned, this is encouraged all over the world. There are global undergraduate awards. Here is one which is instituted in Ireland for innovation, collaboration, ambition, and this is something which many institutions are getting into. Basically, the idea is to aggressively engage more students and faculty in undergraduate, pedagogical, and research projects. So that is something which I would like to very strongly advocate in today's webinar. So here is a research project. This goes beyond pedagogy. This is a new problem which was solved by Narola Harsh Bharat at ICER. This again required a lot of perseverance, learning many new things. Harsh published this in the Journal of Physics recently. And this is an application of a fairly advanced mathematical method in solving problems in pure and applied physics. And in fact, this work is sponsored by an external funding agency. In this case, this is from the MHRD grant administered through the Shastri Indo-Canadian Institute, the SICI or SICI as it is known as. And this project, in fact, continues, and it is an example of what can be achieved during the 4 years. See, look here, the undergraduate career is typically between your age of 17, 18, 19, maybe up to 21, 22, 23 or thereabout. And the learning curve during these 4 years, this is incredible. This is going to set the pace for what you're going to achieve tomorrow. This is going to set, this will give you the momentum of how far you can go in your life and what you can contribute to the society, what you're going to be remembered for. You're not going to be remembered for the jobs that you get or the salaries that you earned. You will be remembered for what you contribute to the society. What is the advancement in science or engineering or technology that you leave, which you create? And this is your ability which will be built through projects of this kind. So the same Shastri Institute has sponsored another project. In this case, this is Akash Yadav from the IIT Tirupati, and he tells us that undergraduate research is a great opportunity to focus on real world issues and work at the forefront in order to make a global impact. Now, this is amazing. This is Akash working with my research collaborator, Professor Sriram Valluri of the University of Western Ontario. This picture was taken at my home after dinner when Akash and Ram were working together. In fact, Aditya was also there. He's not in this picture, but he's on across the table. And Akash went on to publish this last year in the Journal of Physics Communications. It's a very nice piece of work on thermoelectric materials, the figure of merit analysis. And let's hear Akash on this. Yes, Akash.
I believe undergraduate research is one of the most exciting things a student can get involved in. It's a great opportunity to focus on real-world issues and work at the forefront in order to make a global impact.
So this project continues, and we have some other applications being taken up by these young students. They are now in the second year at IIT Tirupati, Sibi Balan and Prabhat. They are working on electronic properties of graphene. So they are working on fairly advanced problems actually. And they are only in their second year today as we talk. And in fact, they have a paper presentation tomorrow at an international conference on nanoscience and nanotechnologies. This is This conference begins tomorrow, 7th of July, goes on till 10th in Greece. And Sibi Balan and Prabhat have done some work which goes into this. This is done in collaboration with scientists across different institutions. They involve Odd Mainan at the University of Grenoble in France, and then Sriram Valluri and Najee Jasravi in Canada at the University of Western Ontario. And they tell us that we understood the importance of collaborative work in research. And let us hear them. Yes, so Sibi Balan first.
The team we are working with are amazing people, extremely dedicated to their work, and their constant enthusiasm and determination is, we think, what keeps us motivated to move forward.
Yes, and working with the team has really been a great experience for us. We were often placed in situations where we had to learn things to keep up with the entire team. They evaluated our work at every stage. They also gave us guidance when we weren't looking the right way. We believe this experience could be a great beginning for our research careers.
So I'm really very fortunate to have been able to get these narrations from these students, and there have been many others who I could not contact, or even after contacting could not insert their narrations in today's presentation. I have enjoyed this very much, and in my mind, the best part of today's narration is the opportunity to celebrate the work done by these students. This is my last slide, because I have really enjoyed working with these students. They, as I mentioned here, they enter college education with dreams in their eyes, questions in their minds, and boundless ambition. So they really achieve so much, and it was a great opportunity. There are some whose narrations I have not presented. There are some others in this picture. There is Pranav Manangat over here, for example. There is Ali over here, who has recently started working on a project in quantum computation. So they take up problems from, Newtonian mechanics to quantum theory to theory of relativity, and work on problems and applications which are of great importance in both fundamental science and also engineering. Like Akash's work is directly related to the efficiency of thermoelectric materials. It has got applications in the energy sector, and so will be the work of Sibi Balan and Prabhat. So there are important and great opportunities of getting undergraduate students, and I'm sure this is practiced in a good number of institutions. There are, I believe, scores and hundreds of other students and faculty members who are involved in similar activities, and I hope that this number grows even further. So thank you all very much. I will be happy to take some questions now. Thank you.
Yeah, thank you so much, Dr. Deshmukh. This was indeed a very nice presentation. So before taking questions from all of you, I would like to take a few questions which came at the time of registration. So the very first question is, despite having good qualification of our professors, why they don't teach us good physics? I think this is a pain point. So yeah.
Well, I think they do teach good physics, and it's not that they don't. And now the sources of learning today are, there are so many alternative sources. So sometimes the teacher is communicating in a manner which he has developed, and you may not be tuned into this. If you're not tuned into this, you can try to listen to some other lecture. There is a lot of excellent material available on the internet. On the YouTubes, there are great lectures. So I think that there is no scarcity of knowledge in today's world. So this question perhaps could have been of some relevance maybe 30, 40 years ago. But I don't think it is of any significance in today's world when access to some of the best courses means all of Feynman lectures are available. There are a large number of other lectures, even courses which are available on the YouTube, and one can. I think that there is no shortage of sources to learn exciting physics. So I don't think that should be a worry. And that said, I certainly would like to emphasize that many teachers do develop new and exciting ways of communicating with students. So I'm sure that that's something which will continue to happen. Yes.
Thank you, Dr. Deshmukh. There is another question by Vipin Bhatnagar. I would definitely like to hear the role of applied and interdisciplinary fields in keeping the physics teaching even more relevant.
Excuse me, I didn't get the...
Yeah. So the question is, I would definitely like to hear the role of applied and interdisciplinary fields in keeping the physics teaching even more relevant.
Oh, absolutely. Absolutely. See, all the new technologies, they come from basic fundamental physics, and nothing in nature is going to happen which is forbidden by fundamental laws. There are conservation laws, for example, and nothing that is forbidden by these laws could happen. So what are the new things that you really want to invent, or which you can, which you would look for? Means I remember this was almost like 40 years ago when, as a postdoc, I attended a summer school in Sweden, and the director of the summer school, Perala Laudin, told us that the 20th century was the century of quantum theory and the theory of relativity. And the 21st and the next century, the 21st century, he said, would belong to quantum biology and the understanding of life sciences at the quantum level. And we are already 20 years into this century. So where are these advances going to come from? They're coming from life sciences, from biology. They're coming from interdisciplinary areas. And see what they need you to understand. They need you to know quantum theory. That means that you should understand differential equations, matrix mechanics, vector calculus. So all this is interdisciplinary, knowledge, which is going to come together. And this is what makes learning basic fundamental physics so exciting, because depending on what path your career actually takes, you might end up making some of the most important advances in quantum biology. Thank you.
Thank you, sir. There is another question by Tushar Rastogi. I am at the age of my UG. What are some tips to increase my learning towards physics? So
well, read a lot, talk to your friends, whatever you have learned, explain it to your friends. Knowledge always increases when you share it. So whatever you have learned, try to explain whatever you have learned to others, and then you will discover that there is more to learn and alternative ways of learning this. So just keep doing this, and I'm sure that you will go a very long way. Yes.
Yeah, so there is another question. This is by Bindya Arora. What is the difference between guiding an undergraduate student and a PhD student in terms of time and guiding techniques?
Good question. And usually I say a question is good when I do not know the answer. Personally, I have never distinguished between undergraduate students and MSc or PhD students. I have enjoyed working with all of them for different reasons. but the level of enjoyment and the level of engagement in this process is pretty much the same. When you're working with an undergraduate student, you're learning with some very elementary but fundamental ideas, which are extremely important. They lay down the foundations of physics. And when you're working with your PhD students, and I have had an opportunity to work with many of them, I have not presented even one of them in today's webinar because I restricted it to my experience with undergraduate students. But indeed, it is very exciting to work with PhD students. And then you're working with a problem. And what is exciting about it is that your student is going to find an answer to a question for which nobody else knows the answer. Your student will be the first one to get that answer. And it is for this that he will publish his result and get a PhD. So it's very exciting that your student is going to be the very first one to get an answer to some question which humanity doesn't have an answer for. So you get excited and you get engaged in PhD research for a different reason as you get for undergraduate pedagogical projects, but the amount of excitement and the engagement that you experience in working with them is pretty much the same in the sense that, okay, you can't say that, okay, this is better than the other. I don't think I could ever make this distinction, at least at a personal level. And that's part of the reason that I have easily worked with as many undergraduate projects which have actually led to some kind of publication as the number of PhD students perhaps, which I have guided, which is not a whole lot. It's both are small numbers, but they're pretty much even. Thank you.
Yes, sir. So just a second. I'm just going through the questions. So next question is about your book, Foundations of Classical Mechanics. So Vijay is asking, have you used your personal experience related to these students' projects in your book, Foundations of Classical Mechanics?
Oh, certainly, yes. And it was easy to do that because their projects, most of these projects have actually led to publications in pedagogical journals like Physics News, Indian Association of Physics Teachers Bulletin, Resonance. And sure enough, you have these students whose work I talked about, Parth, Habiya, Vaishak, Kaushal, Jnaneshwari, Niharika. So all of these projects, Gopal and Satish and Venkatesh, all of their projects have found mention in my book. And what I enjoyed very much is, writing a book on a classical subject like, Newtonian physics, Lagrangian physics, Hamilton's physics. This physics has been there for hundreds of years. And thousands of books have been written on this. So where is the challenge when you want to put across these ideas in a novel way? And my ambition was to speed up these students from the physics of Galileo, Kepler, Newton, to bring them in quick undergraduate semesters to advanced physics so that they get ready for quantum theory, they get ready for theory of relativity. So this needed to be done in a very rapid and accelerated manner. So the projects which these students have done enabled me to attempt that. And this attempt is reflected in this book. And sure enough, the papers that they have written have been cited in this book. And I hope that both students and teachers will enjoy reading this book. Thank you.
Thank you so much, sir. There is another question by Ankit. How can a student from local college be encouraged for research?
Oh, Vivek is a great example. You have him in this picture. It is here. I mentioned that he was an undergraduate student at Amrita University at Coimbatore. He went to his physics teacher and said that he wanted to do some physics research project. His teacher happened to be a former student of mine who did MSc in physics from IIT Madras. Good friend now, Subish. All of my other students know him very well. And Subish asked Vivek to come to IIT Madras. And there is always somebody who is known to somebody you know, who will help you out. So go and talk to people, talk to your friends, talk to your teachers, tell them that you want to get involved, write to them. If you don't know anybody, just get their email address of some teacher from the internet, write to him, tell him that, yes, I want to do this work. Can you help me out? I get these emails even today. And indeed, we do look for an opportunity to work with students. We are always looking for students who are interested in doing projects of this kind. So there is absolutely no stopping. Just talk to your friends or send an email and say that this is what I want you to do. Maybe sometimes you won't get a reply. Send another email. You don't get a reply the second time, send a third one. I'm sure you will get a reply, and perseverance is an important part of this. So I'm sure that you will get a break. Yes.
Okay, sir, there is another question. This is by Rucha. Rucha is asking, sir, what should be typical duration of a project? 1, 2, 3 to 4 years. I think she's asking about typically how much time is required for the completion of a project.
Well, I don't know.
It actually depends.
Yes, it depends on the nature of the project, and depending on your other commitments. I know that these things cannot be done at the cost of your regular college studies. You have your exams and you need to do well in those exams. So you can't and shouldn't, let that get affected while you get involved in a project work. But depending on how far you can go, there is no end to learning. Means I remember I attended one concert by Shiv Kumar Sharma. It was a Santur concert, and Shiv Kumar Sharma was telling about the music that he learned. And what he said is that सिखाने की तो सीमा होती है, लेकिन सीखने का कोई अंत नहीं होता. What he meant is that there's only so much you can teach, but there is no end to learning. So when you take up a project, you can keep learning, you can keep getting deeper into it. And I don't think there is a limit to that. So you can take up projects which can be done in a month or 2 or 6 months or a year. Vivek worked for practically 4 years, but he published 2 good papers. Abia has worked on this chaos in chemical reactions for something like 2-3 years. And it's not that this is continuous work, because this is done part-time with no specific strict schedule, but this is done only out of passion for work. And you give as much time as you can afford, go as far as you can go. So don't look for the limits. Just keep exploring and enjoy the journey. Thank you.
Okay, sir. So this is the last question for today's session. This is very interesting. This is my personal observation. These days, most of the universities are hiring researchers for teaching positions. But these high-profile researchers are not able to create any interest in subject teaching. What's your take on this? Why universities are looking for high-profile rather than teachers, high-profile researchers, he might be asking. Teachers and researchers are vice versa or not? I would like to hear from you.
Again, this question sparks a lot of controversy. Personally, I do not subscribe to these alternative views, because I think that most of the good researchers either are or at least can be good teachers, and also vice versa. So I don't think that there is strict partition between abilities to teach and abilities to carry out research. I think that they go together. And in a university system, in an academic institution, I know there are research institutions which are purely research institutions, and teaching is not their priority. So there you have most of the scientists are carrying out pure research. But in most of the universities and most of the institutions like the IITs, we are engaged in both teaching and research. And I believe that both of these are intrinsic and equal components in one's professional career. So they do go hand in hand. They ought to go hand in hand. Sometimes some faculty members devote more time to research than to teaching. But I don't think that that should be done. That's my personal opinion. And you will have to ask them, ask those faculty members who don't do this. They would be the ones to ask this question. But personally, I think that both are important and equal aspects of a faculty position in a university system, because teaching and research both are not separable in an academic institution. Yes.
Thank you, Professor Deshmukh, for agreeing to conduct this webinar for us. And I'm also thankful to audience for joining in big numbers and asking interesting questions. The participant might receive a feedback email. Will be encouraged to receive your valuable feedback. This session will also be available on Facebook and YouTube for those who want to revisit and want to circulate this amongst their friends. Thank you once again. I would also like to mention that Professor Deshmukh's book, Foundations of Classical Mechanics, is available on open access till 10th of July. So I encourage you all to visit cambridgescore.org and make most of it. Thank you so much.
So may I stop sharing the screen now?
Yes, sir.
Okay, and then I can go ahead and leave the meeting, right?
Yes, sir, you can leave the meeting now.
Okay, thank you very much.
Thank you,
All the
everyone.
hosts, all of you out there at the Cambridge University Press, I'm really grateful to all of you for the support and the wonderful opportunity to work with all of you. Thank you. Goodbye.
Thank you once again. With this, we sign off. Thank you so much.
Yes.